Hi there! Resistance measurements taken with a multimeter or a dedicated ohm-meter may sometimes carry a huge error, difficult or impossible to eliminate with typical two-wire probes measurements. Back in 1867, William Thomson, alias Lord Kelvin, put together a method that makes use of 4 wires to measure a single resistance. The method that he perfected eliminates the majority of the problems of the two-wire method and decreases considerably the measurement error. Let's see what is that all about. Let's start with the typical resistance measurement taken with a multimeter. One way to measure the resistance of a resistor, no pun intended, is to take the resistor and connect its leads to the probes of a multimeter set to measure resistances. Then you read the resistance value on the display. But is that an accurate measurement? Well, yes and no. It depends on several factors. Let's dig into it a little bit to understand what I mean. We can draw a diagram of the setup for measuring a resistance. Such diagram would be something like this. RUT is the resistor under test. The one on the left is the multimeter set to measure ohms. RD1 and RD2 represent the cables of the two probes connected to the resistor. Such cables are made of conductor, most like copper. However, as good as copper can be as a conductor, it is not a perfect conductor, and therefore each of those two cables have a resistance, which I have called RD1 and RD2. So the ohm-meter, when measuring the resistor RUT, it is actually measuring a series of 3 resistors, RD1, RUT and RD2. Now, if RUT is much greater than RD1 and RD2, then these 2 additional resistors become negligible compared to RUT, and so they cause only a negligible error on the measurements. But if RUT is just 1 or 2 orders of magnitude above RD1 and RD2, the error is not negligible anymore. Let me explain in a little more detail. First of all, we need to define the error when measuring a resistance. Starting from the diagram we have just seen, we can write down this formula. Let's make an example to clarify how to use this formula and what does it mean. Let's assume the probe cables have each a resistance of just 0.2 ohm. After a few adjustments to the previous formula, we can come out with this other one much easier to use, that the error equals 400 divided by the sum of RUT and 0.4. Let's calculate now, based on this formula, the errors made while reading a number of resistors, so we can make some comparison. So, with a resistor of nominal value of 100K, the error is just 0.004%, very small. But with a resistor of 10K, the error increases to 0.04%, still small, but 10 times more than the previous one. And with a resistor of 1K, it becomes 0.39%. So look how much the error becomes for even small resistors now. 38.5%, 285.7%, and even 800%. So you understand now how the measurement of small resistors becomes totally useless with this method. So the smaller is the resistor to be measured, the greater is the error, and that error becomes huge for very small resistors. In fact, the error is inversely proportional to the value of the resistance being measured. And that is bad, also considering that the error is not always the same, but keeps changing with the measured resistance itself. Well, it is obvious that we need to eliminate such an error, otherwise it becomes impossible to measure small resistors. Fortunately, the solution is very simple, and it was provided to us a long time ago, back in 1867, by William Thomson, known also as Lord Kelvin. The method is basically to use 2 instruments at the same time, an ammeter and a voltmeter, along with a power generator. The generator injects a current into the resistor. We measure the current injected with the ammeter, and we measure the corresponding voltage at the resistor leads obtained by Ohm's law. Once we know both voltage and current, we can divide the first with the second and obtain the resistance. There are also some digital multimeters that do all of this on their own. They generate internally a specific value of current using a current generator, and such current is injected using two wires connected to the resistor. Then, two more wires are connected to other sockets on the panel, and from there, the multimeter measures the voltage across the resistor, calculates the value of the resistance, and visualizes it on its display. And this is much simpler than using two separate instruments and then do the calculations by hand. Here is a diagram representing this method of measurement. The device on the left is the current generator, connected directly with two wires to RUT, the resistor under test. Such wires each have their own resistances RD1 and RD4. The voltmeter, also on the left side, is also connected with its own two cables to RUT. Each of its cables has a resistance RD2 and RD3. Okay, now don't say that we made things worse because now we have two extra resistances and a more complex circuit. Please bear with me for just a minute. First of all, let's consider RD1 and RD2. These two resistors are in series with the current generator, which provides a known constant current. Therefore, no matter the value of these two resistors, the current through RUT will always be the same. And, because of that, the ratio between the voltage across RUT and the current through it will be a constant, and that is the value of the resistance we are looking for. Therefore, the resistance of the two cables connecting the current generator and the resistor under test do not interfere with the measurement. Now, let's talk about the other two resistances, RD2 and RD3. These resistances are in series with the voltmeter. If the voltmeter has a high input impedance, and since RD2 and RD3 are very low because they are just the resistance of the cable probes, these two resistances are negligible compared to the voltmeter internal resistance. Therefore, they don't play a role in the measurement of the voltage across RUT. Well, look at that! We have 4 cable resistances in this measurement model, but they don't introduce any error. So, what is causing a measurement error in this configuration? There must be one, right? Well, it is just the intrinsic error of the current generator and the voltmeter combined together. And since the two devices are totally uncorrelated, the total error is the root mean square of the single errors. So it is way within our control. Moreover, if we use a single DMM with 4-wire resistance measurement capability, such instrument will come already with its total error for this kind of measurements, so we don't even have the need to calculate it. We just connect the cables, we measure the resistance on the DMM display, and we know what the error is. For example, the instrument I am using has a declared error of 0.05% when measuring resistances. Think about it. It is an error of 0.05% regardless of the value of the resistance. Isn't that cool? True, such instruments are kind of costly, and additionally they need to be professionally recalibrated every 2 years or so to make sure they keep their precision, but that's another story. So now, to complete our discussion, let's run a comparison between the measurements taken by a regular multimeter with 2 wires and by a professional DMM with 4 wires capability. I have put on this breadboard 4 different resistors of different value, higher to smaller, from left to right. I will use these 4 resistors to run a comparative analysis of this multimeter and the DMM over there. Let's begin with measuring the first resistor using a 2-wire configuration using the multimeter. And the measured value is 99.5 kilo-ohm. Let's now repeat the measurement using the 4-wire configuration and the DMM. Remember, we need to connect the wires so that black stays with black and red with red. The resistance value this time seems to be a little lower, 99.26 Ks. Be aware that the precision of the DMM is 1 order of magnitude higher than the one of the multimeter, which we can infer from the provided number of digits. All in all, The readout from the multimeter is a little higher than the one from the DMM. Let's repeat now the process with the second resistor. I have chosen it to be 1 order of magnitude lower than the previous resistor, and the result with the multimeter is 0.989K, or 989 ohms. With the 4-wire configuration instead, the reading is 0.9846K, or 984.7 ohm. Again, the DMM measurement has one extra digit of precision, but otherwise the two measurements are very similar. Going to the third resistor, the multimeter reads 10.5 ohm. But you can see now how the last digit keeps changing, and the reason is that the resistance of the connection of the cables keeps changing slightly depending on the pressure I exert on the probes. We can already understand how a 2-wire measurement in this condition is less reliable than the previous two. But let's now repeat the measurement with the 4 wires and the DMM. And we find a readout of 10 ohm, 10.00 after the reading stabilizes. Can you see how stable is this reading compared to the previous one? That is essentially because with the 4-wire configuration, the resistance of the cables don't play a role anymore. Let's measure now the last resistor with the multimeter. And the value is something in between 1.1 and 1.3 ohm. Do you see how huge is this error now? However, if we repeat the measurement with the 4-wire configuration, here is what we obtain: a very stable 0.96 ohm. We can conclude that as long as the resistances being measured are above 10K, the cable resistances do not cause much harm. In fact, they do not add up too much to the resistance in percentage, nor they produce a big error. However, for resistances below the 10K threshold, things start to degenerate quickly when using a 2-wire configuration. And that is when the 4-drive configuration comes to the help. Of course, you can still measure resistors smaller than 10K with a 2-wire configuration, but that's only if you just need an idea of what the actual resistance is. If you need instead a precise measurement for resistors smaller than 10K, you should always use the 4-wire configuration. I hope you found this video both interesting and useful. Please let me know in the comments what you think about it. And because we are at that moment of the video, I'll quickly remind you to subscribe to the channel and to enable the notifications if you haven't done so already, so you won't miss any future episode. I'll see you in the next video, and in the meantime, happy experiments!